Hi everyone, Mr. Smith here, and in this video lesson, we're going to talk about mass-energy equivalence, which maybe is a fancy way of saying we're going to chat about Einstein's famous equation, E equals mc squared. We're going to go into more detail with it. It has a more general form, and then we're going to start looking at some applications of E equals mc squared. So let's get started. So just to preface before we begin the lesson, if you haven't checked out Einstein's Big Idea, the NOVA documentary, I have it posted under day 14 stuff, I believe. But you should definitely check it out. It has a lot of history behind Einstein's personal history and his work history, and it ties everything together that kind of led up to E equals mc squared. But the very last kind of arc of the show focuses on a scientist, Lise Meitner. And it's a very fascinating arc because her arc takes place during, talk about like it's an anime or something, but she was doing her work during the lead up to World War II. And she was Jewish and she was working in Germany. So there's a whole bunch of tensions there. But she was performing this kind of work here. So what she was doing was she was taking, and her colleagues were taking very large atoms, so atoms with really big nuclei. So they have lots of protons and lots of neutrons. And what they were trying to do is they were trying to fire more neutrons, a few more neutrons, trying to fire it in. And if they can make these new neurons, a neutron stick, then they would have something new. They'd have a new isotope. And who knows, maybe, different isotopes of things have different properties for medicine, for business, for space exploration. So, it's something that interests a lot of people. But what they found was that as they were bombarding their nuclei with neutrons, they weren't getting bigger atoms. In fact, they were getting different elements altogether than what they were working with. And they were thinking, well, how is my work being contaminated? Because I'm firing neutrons at, say, like a uranium nucleus, but then I'm getting radon and krypton and how is this happening? Where are these other elements coming from? And eventually they figured out that their work wasn't contaminated. It was that these bigger atoms that they were working with had actually split into two. And looking at the mass of the bigger guy and the two smaller guys, they can see that the mass of the bigger guy was more. Mass was lost, and that change in mass went to the kinetic energy of those daughter particles flying apart, and they essentially split the atom. But the Einstein's famous equation, E equals mc squared, kind of put all the final piece in place. And you can imagine at this point, having realized that, well, we can split a uranium atom and have, daughter particles flying off at incredibly high speeds that can collide with other atoms, and then those fly with high speeds and start a big chain reaction. This kind of triggered the race for the nuclear bomb. So Einstein's equation states that mass and energy are one and the same. They are equivalent. They can be converted between each other. So mass can become energy, and energy can become mass. And the proportion that ties it together, c squared, is very massive, 9 times 10 to the 16. So when you convert just a small amount of mass to energy, it's a very large amount of energy, comparatively speaking. Now, Einstein's famous equation actually has this form, E equals gamma mc squared. And this equation gives the total energy of a particle. If we think about when what would happen if a particle was at rest when V equals 0? Remember, if V equals 0, then gamma equals 1, and then we get E equals mc squared. And this is called the rest energy. So Einstein's equation gives you the rest energy of a mass. Moving particles have more energy according to E equals gamma mc squared. You can see from this equation, if you let V get really close to C, then gamma, as we've seen, gets very, very large as well. And the energy approaches infinity. It just keeps going forever. This equation actually shows you it's actually impossible for, because it's impossible to plug in V equals C here. You just keep getting higher and higher values for gamma. The energy of a particle is just going to keep increasing indefinitely without ever actually hitting the speed of light. And you can't do it. It requires an infinite amount of energy. This equation kind of shows that. So we're going to play around with E equals mc squared a little bit. So let's do a problem here. We're going to take a 50-gram pencil, and we're going to see how much energy would be released if we could convert everything, and maybe that pencil you're working with, if we could just convert that into energy. So we're going to compare the energy we get to a nuclear bomb yield. Because if you plug in mass in kilograms and C as meters per second, you're going to get joules. And it's just going to be such a high amount of energy that it's going to be hard for us to actually put that into context. So we're going to compare it to a nuclear bomb yield. A nuclear bomb is about 1 kiloton of TNT, which is in itself 4.1 terajoules. And a terajoule is a million joules. A million is a trillion joules. And it's 10 to the prefix tera means 10 to the 12. So let's play around with this. So 0.05. So we'll get the joules first and then make a conversion. And then for C squared, you can do 9 times 10 to the 16, or just 3 times 10 to the 8 squared. So this will give us our answer in joules because we're doing kilograms, meters per second. So 4.5 times 10 to the 15 joules. So let's set up a little conversion chain to make this sink in a bit more. So for some of you, you might need not to show as much work here, but if you want to convert that to terajoules, so 1 terajoule is 10 to the 12 joules. So we're kind of multiplying. This is basically 1, right? Because 1 terajoule and 10 to the 12 joules are the same, but it has the nice effect of converting that into terajoules. And then we have 1 kiloton of TNT. I'll just say KTNT. We said was 4.184 terajoules. And then those are equivalent, but the units will cancel. So we're going to take 4.5 times 10 to the 15, divide by 10 to the 12, and then divide by 4.184. So when it comes out the other end, you've got about 1,076 kilotons of TNT. So almost over 1,000 nuclear bombs just from unlocking all of the mass in your pencil. So that's pretty crazy. That's a lot of energy. Now, when we talk later on today about fission, nuclear fusion, radioactivity, the change in mass is going to be extremely small, fractions of the mass of a proton and neutron. So the energy we release in those will be fairly small. But yeah, it's amazing how much energy is locked in mass. Right, so this brings us to this idea of relativistic kinetic energy, because we have the rest energy equals mc squared. You have the total energy for a particle, gamma mc squared. So the difference must be the moving energy to the kinetic energy. So classically, when we're moving at speeds that are much less than the speed of light, using 1/2 mv squared is totally appropriate. But when we have speeds that are close to the speed of light, we need to use an updated version. And we get the kinetic energy again by taking the total energy minus the rest energy. And so this factors into gamma minus 1 mc squared. So let's find the relativistic kinetic energy of an electron moving at 0.9 C. So first of all, let's find gamma. And we'll use we've done enough of these. Hopefully you're just putting this into practice too. When we plug in 0.9 C, it's going to be squared and the C's will cancel out. 1 minus 0.9 squared. I got 0.19, but I feel that's low. What did I do wrong? 1 divided by 1 minus 0.9 squared. That's better, but 2.3. So the relativistic kinetic energy, 2.3 minus 1 times the mass of an electron, which we know is 9.1 times 10 to the minus 31 kilograms, times 3 times 10 to the 8, all squared. So let's crank this out. 1.3 times 9.1 x times 31 times 9x 16. And I think maybe let's compare this with, so I got 1.06 times 10 to the minus 13 joules. That was the relativistic one. Let's just quickly, just for fun, I don't think I asked you guys to do this, but let's just actually check it out. Let's find what it would be using the classical formula. 9.1, times 10 to the minus 31, and then v squared. So that would be 0.9 times 3 times 10 to the 8, and then we're squaring that. I just would think it's interesting to see this. So 0.9 times 3x 8 equals squared. 2 equals times 9.1 x minus 31. So I got the same as before, 3.32 times 10 to the minus 14 joules, which is actually a lot smaller. And I'm just going to divide the bigger one by the smaller one to see how much smaller. Okay, so about 3 times as small. So that's significant. That just can't be ignored. So yeah, hopefully you're convinced, for things moving close to the speed of light, we need to update how we calculate kinetic energy. It makes a big difference. All right, let's keep moving. You may have noticed, but the energy we calculate in that question is very small. An electron, even a moving electron moving very fast, doesn't have a lot of energy. It's a very small amount of energy. And when we talk about like the mass of a proton or an electron is very small, but when we actually talk about mass loss in like nuclear fission and radioactivity, the changes in mass are even smaller than the mass in an electron. And because we're working in small masses and small amounts of energy, there's a couple units we're going to make use of. One is the electron volt, and the other is the atomic mass unit. So 1 atomic mass unit is about this many kilograms. And then we've kept a lot of accuracy here because we're going to use this in a derivation. But you can think of it as roughly, and again, this is not precise, you can think of it as roughly the mass of a nucleon. And a nucleon is just a proton or neutron. Now, neutrons and protons have different masses, but they're very close to 1 atomic mass unit. The electron volt is the energy required to move an electron through a potential difference of 1 volt. And that's the definition of the electron volt. So often in your work today, you're going to see the units of energy as electron volts, or maybe mega electron volts, million electron volts. And in our work, when we're looking at changes in energy for nuclear reactions, we'll be using atomic mass units instead of kilograms. And why we're going to do that will hopefully become apparent here. We're going to find a useful conversion right now. So we're going to start off by looking at the energy equivalent to an atomic mass unit. So energy using Einstein's equation. Energy equals mass times c squared. And here for the mass, we're using 1 atomic mass unit. So 1 atomic mass unit was 1.660538 921 10 to the minus 27 kilograms. And the speed of light, more precisely, is 2.9979458 times 10 to the 8 squared. So let's find the energy there, and let's keep as much accuracy as we can here. So I've done this earlier, but I always, I've done this countless times, but I always do it while I'm doing it during teaching a lesson, just out of habit, just to, just make sure I catch mistakes, make sure I know what I'm talking about. And I got the same thing as before. So I got 1.49 2439082 times 10 to the power of minus 10. And this would be joules, because I did use kilograms and meters per second. So we're going to make a little conversion here. We're going to convert that to electron volts by using the value on the previous side. We're going to divide the joules we have by 1.602, etc., times 10 to the minus 19 to get the electron volts. So if you might do this, times 1, I'm going to show this work, times 1 electron volt, and 1 electron volt is 1.602 17653 10 to the minus 19 joules, and so those are going to divide out. Let's give that a go. All right, so and at this point, I feel safe to do some rounding. So what you get is about 9.315 times 10 to the 8 electron volts. So that's a lot of electron volts. So we actually reduce that to, or we make it smaller by using mega electron volts. So 1 mega electron volt is 1,000,000 electron volts. So we divide that by 10 to the 6, and we get 931.5 mega electron volts. And maybe you're thinking, so what? How does that help us? Well, if we rearrange this equation, so the energy is 931.5 mega electron volts, and that equals UC squared. If you rearrange that for U, you get U equals 931.5 mega electron volts divided by C squared. And why is that useful? So what later on, when you're setting up E equals MC squared calculations, if you plug the mass in as atomic mass units, you're going to get over C squared dividing out with the C squared, and you'll be left with mega electron volts. So it's a very quick way to go from atomic mass unit to mega electron volts, essentially multiplied by 931.5. Now, I teach this once a year for the most part. And I believe like some resources might have 931 or 932, but we're going to stick with 931.5 mega electron volts per c squared. And so most of our work moving through the rest of the day is going to be focused on nuclear reactions. Just like in Einstein's big idea with Lise Meitner, during nuclear reactions, the mass of the products is always a little less. And that change in mass comes from E equals mc squared, and that mass is converted into energy. So kinetic energy of the particles flying, the daughter particles flying apart, maybe some heat. So let's do a few examples. So if you want to pause this one and give it a try. Now we are just doing another example, but instead of a 50-gram pencil, it's a 10-kilogram cat. And here we're going to say an atomic bomb is actually about 20 kilotons, whereas before we said an atomic bomb is 1 kiloton of TNT. And there's definitely there's small atomic bombs, there's very large atomic bombs. Let's do, so this one, let's just play around one more time with E equals mc squared. Like most of us can now put this into perspective. Like you can look at your cat or your small dog next to you and think, what would happen if I were just to convert you all into energy? So 10 kilograms, and we'll work with kilograms meter per second. That's going to give us joules for now. That's 9 times 10 to the 17 joules. And then you can set up your conversion chain. 1 terajoule, 10 to the 12 joules. And we said that 1 kiloton of TNT was 4.184 terajoules. And now we're saying one bomb, we're saying, did I have that? Oh yeah, that's fine. Yeah, one bomb is 20 kilotons of TNT. And so all the units are going to divide out. And so we're going to multiply, or so we're just going to divide by 10 to the 12, 4.184, and 20. Okay, so that's a lot. That's like basically 11,000 bombs. Think of it, your 10-kilogram cat next to you is like 11,000 nuclear bombs. That's a lot of bombs. All right, a second example. Now, this is a fresh example I cooked up this year, so we'll see how it goes. We are going to talk about radioactive decay in a later lesson, 2 lessons from now. But most people have an idea that very large, unstable nuclei kind of decay and emit, for lack of a better word right now, radiation. But subatomic particles decay too. And actually the neutral pion, so it's a subatomic particle, I think it's made of 2 quarks. But when it decays, it loses all of its rest mass. It's just gone. And its rest mass goes into, it actually decays into 2 photons, I believe. But all of that rest mass is gone because photons have no mass. All this rest mass goes to energy. And the reason I want to do this example, because often when you're looking up masses for subatomic particles, they're going to be in this weird unit, mega electron volts per c divided by c squared. So I wanted just to do an example to give you an idea of like how to find that mass in atomic mass units and kilograms. So this will just be a quick example. Now, it's actually probably easiest to find the energy release right away. It's actually very quick to do. So using E equals mc squared, the mass is 135 mega electron volts divided by c squared times c squared. And so you can see how convenient having this unit for mass is. the energy released is just 135 mega electron volts. As far as what its rest mass is, so we said that U equals 931.5 mega electron volts divided by c squared. So I can rearrange this. That means that 1 mega electron volt divided by c squared equals 1 over 931.5 U. So let's actually check out the mass, just doing a little conversion. So the rest mass is 135, and every mega electron volt divided by c squared is 1 over 931.5 atomic mass units. 135 divided by 931.5. So we get about 0.14 atomic mass units. And that would be fine. Often we actually state the mass of things in terms of atomic mass units, but we can just go one step further. We have that conversion from earlier. 1 atomic mass unit was 1.66, and I think I'll just use 1.66. We don't need to be super precise here. We were really precise earlier in that derivation because we wanted a really exact value for if we had used less, if we didn't round as much, we'd have something significantly different than 931.5. So about 0.23. I was like, that's way too big. That's because I forgot to multiply by 10 to the power of minus 27. Mm-hmm. 10 to the power of minus 27. Okay, so that's better. So that's 2.3 times 10 to the minus 28 kilograms. Very, very, very small. But yeah, I did want to just touch on that because I know like when I'm developing content for this unit and I'm, trying to create maybe a nuclear fission example or radioactivity example, and I want to look up the mass of an isotope or something like that, it's often given in either atomic mass units or for very small things, mega electron volts over c squared. So just wanted to do an example, tying some things together, mixing some things up, broadening your horizons a bit. All right. And the last example we'll do together is just an example working with the electron volt. Again, because often the energy involved in very small particles is really so tiny, we like to use different units for that. So we've got the electron volt. So we have an electron moving at 0.86 C in a laboratory. We're going to find its rest energy, its total energy, and kinetic energy in electron volts. So let's find its total energy, and its total energy is gamma mc squared. And then we'll find its, I'm just going to set the problem. We'll find its rest energy, and that's just given by mc squared. And then from there, we'll be able to find its kinetic energy too. So just aside our usual calculate gamma. One divided by the root of 1 minus 0.86 squared. So a gamma factor of about, basically 2, but I feel I'm just going to use 1.96. We got 3 sig figs in our speed, so I'll use 1.96 for gamma. So the total energy is 1.96 times the mass in electron, 9.1 times 10 to the minus. Now we can probably use 9.11 because we have 3 sig figs in the speed. And the speed of light, 3 times 10 to the 8 squared. So keep in mind, this is going to give our answer in joules. And then we'll just divide by the conversion for electron volts. So that's about 1.61 times 10 to the minus 13 joules. And if you divide that by our value from earlier, and some of you guys may have noticed that this value, it's actually the same numerical value as the charge on an electron, or the elementary charge. So if you divide that by 1.602 times 10 to the minus 19, we get about, what I'm working, yeah, I think I will. So I got about 100,000, or sorry, I got about 1 million. Yeah, it's pretty close to 1 million mega electron volts, which is equal to 1 mega electron volt. So let's just do that for the rest of them, and then I'll make up my indecisive mind later whether I want to use electron volts like the question asked, or just keep it in mega electron volts. All right, let's do the rest mass. So the rest mass, 9.11 times 10 to the minus 31 times c squared. This will give us the joules, times 9x16. So basically 8.2 times 10 to the minus 14 joules. Divide that by the elementary charge. So this one, you get about 512,000 electron volts, which is equal to about 0.512 mega electron volts. And that means the kinetic energy is the difference. And I know the question said do it in electron volts, but I just like mega electron volts better. So it's the total energy minus the rest energy. So 1 minus 0.512, 0.488 mega electron volts of energy, or 488,000 electron volts. All right, so we have now played around with atomic mass units, electron volts, mega electron volts. We looked at the energy conversion for fairly large masses and little masses too. And the major thing that we'll be using for the rest of the day is this conversion right here. So we've derived that too, and it's ready for us to use to study some nuclear physics. So in our next lesson, we're going to use E equals mc squared to look at nuclear fission and nuclear fusion. It should be a lot of fun. I'm looking forward to it. So hopefully that lesson kind of helped you out a little bit with units big and small. And we're now ready to go to do some cool applications for our final 2 lessons. But that is it for now. Hope you guys are staying well. Have a great day, and we'll see you soon.